Hello all, I'm Emre Erçelik. In this short video series, we will take a look at a specific problem occurred in the ME362 course project, and we will solve the problem. We will then take a deeper look at the theory of the solution, example applications, and a real application. This is the first video of the series. You can find other 3 videos also in the channel. We will start with the problem definition and understand the origin of the problem. The topic is why stress-strain plots are discontinuous. Let's start with the definition of a Gauss point. Gauss points are where the calculations take place. Stress and strain. First Gauss point is a real point in natural space, and natural space is defined by xi and eta. This coordinate system is just like Cartesian coordinate system defined by x and y. If you calculate a function at a Gauss point, it outputs a value. Consider the coordinate created by x, y, and fxy in the Cartesian coordinate system. This point represents 2 coordinate values and the output value in 3-dimensional coordinate system. In our course project, we calculate stress and strain of a plate but on natural space. Where are the Gauss points in the code? The Gauss points are stored in Gauss point function. This function stores literally the same numbers with the table. You can compare the first Gauss point and the Gauss point function, as you can see. The function just returns the same data with the table. The aim of this function to get a specific Gauss points data. So I mentioned an analogy with the Cartesian coordinate system. Where is the analogy in the code? The analogy is in your element postprocess function. For every Gauss point and element, a loop runs. We calculate epsilon, which is strain, with the information provided by the Gauss point. You can see the 408th line. We use Gauss point to calculate strain. After calculating strain, we calculate the stress with the formula sigma equals to Young's modulus multiplied by strain. You can see the equation in line 415, and you know this equation from Mechanics of Materials 1 and your finite element course. And done. This is the meaning of stress and strain are calculated at Gauss points. You use Gauss point data to calculate a specific function. In summary, in the code, Gauss points xi and eta values are used to calculate a particular function. The functions are stress and strain. Therefore, your function's value is output at Gauss points xi and eta coordinates. We assign calculated values in an array. This is called global stress and strain data. And this storage takes place in the lines 421 and 422. Then we use these large arrays to plot our calculations in post-process function. Now we are slowly moving on to the problem. We will try to understand the problem on natural space. We calculated stress and strain functions at Gauss points. And Gauss points are defined inside of an element. Inside values should have been plotted inside coordinates. This is the correct logic. However, this functionality does not exist in Matplotlib or Paraview. Instead of doing this, we move the Gauss point data to the nodes. Result is you visualize the value where it is not calculated at. Consider this simple example. Orange dots represent the nodes, green dots represent the Gauss points. We visualize green values at orange's coordinates. In other words, we are visualizing the values at the coordinates they are not supposed to be. We are moving the visualizing places as shown in each arrow. Now we will take a look at the problem in physical space. Gauss points correspond to blue circles, and the code calculates the stress and strain exactly at blue circle coordinates. However, because of lack of functionality in plotting software or library, we plot them at nodal coordinates in the orange circle n. Consider the arbitrary composition of 4 linear quadrilateral elements, or in other words, D2Q4n. This structure is completely arbitrary. Assume that it was taken from a real analysis. We focus on the structure and only investigate 4 elements only. Every element has 4 Gauss points, 1, 2, 3, and 4, shown with the blue circles. Orange node n receives 4 different values from 4 different elements, whereas it should have only gotten 1. A point must represent only one value, not 4. And finally, this is the reason of discrete plots. An example is given in the right side. But what about displacements? They were as smooth as possible. You must heard of the displacements are calculated at nodes. We calculate them at nodes and we plot them at nodes. In this situation, nothing is problematic. Remember the formula below, which we use in our hand calculations. This is the calculation of displacements. You can see the line 61. The process is completely on nodes. There is no Gauss point loop. This is the same process with your hand and paper calculations, but in the matrix form. You calculate every node's displacement, then plot them on the node coordinates. Therefore, the plot is smooth. Now you must have understood the reason behind discrete plots. The summary of the reason is we are plotting some values calculated at point A, in this situation Gauss points, but visualize them on point B, on node coordinates. The next question is how to smoothen. You can proceed to the second video of the series.